All right, so we're gonna move on from trigonometry. Well, not we're gonna move on from trigonometry, but we're gonna keep on doing trigonometry. But we're gonna move to a kind of a new subject, which is not directly tied to trigonometry. It's not an essential part of trig. It's more like an application of trig. And the topic is called polar coordinates. So when we talk about coordinates, we usually think about x coordinate, y coordinate, because that's the coordinate system we've been using pretty much this entire time, right? That's called the rectangular coordinate system. And the rectangular coordinate system is good and useful when you have a flat plane. Now, on the surface of the Earth is not flat, the Earth is round. And so on the surface of the Earth, we're never technically dealing with a flat plane. However, for regions on the Earth where you've got lines of latitude and lines of longitude going horizontally and vertically here, for regions on the Earth where you're like closer to the equator, right, or just somewhere in the realm on the side of the Earth, if you will, then the way the lines of latitude and longitude cross each other and the way that grid lays out is not exactly flat, but it's pretty darn close to flat. So over here, if you're in Africa, or North America, or even Europe, or anywhere really, the like rectangular coordinate system turns out to be like a good approximation, a good thing to use if you're going to like draw a map or something like that. And the rectangular coordinate system kind of roughly aligns with the idea of latitude and longitude. However, if you are near the poles, right, either the South or the North Pole, then what happens is the lines of longitude come together, right? The lines of longitude all come together at the pole, and the lines of latitude are actually circles, right? They form circles around the pole. So you get this thing that looks kind of like a spider web. And so up at the North Pole, it doesn't make sense to use a rectangular coordinate system any longer. What it would make sense to do is use a different type of coordinate system, one where you have lines radiating away from the origin, and you have circles, concentric circles, centered at the origin. Okay, and then you measure your location not by the x-coordinate and the y-coordinate, but instead by the distance you are away from the pole, right? So the distance from the origin, the North Pole in this example would be at the origin. And then some sort of a direction, from, maybe measured from the international dateline, or perhaps the Greenwich meridian. And that would be like an angle in theta, perhaps in standard position. So that's called a polar coordinate system, and it was developed by sailors when they were trying to navigate, trying to find a northwest passage. They were trying to navigate up here around North America and trying to get to the other side so they could get to Asia. And all that navigating they did near the North Pole, they needed a coordinate system that was appropriate for them. So that's how the polar coordinate system was developed. Now so I've drawn these pictures. The rectangular coordinate system has its x and y axes, and the way we are going to build the polar coordinate system is actually in the same. It's kind of like on top of the rectangular coordinate system. So I drew the x and the y axes again over here in purple. But then kind of superimposed on top of that x and y axis, we're going to have radiating lines coming out from the origin and circles centered at the origin. And so a point in the xy coordinate system also exists in the polar coordinate system, and vice versa. It's like this, we're going to have the exact same flat plane in both cases, except that we're labeling points with xy in one case, and we're labeling points with r theta in the other case. R stands for radius, and theta stands for an angle. So let's draw. Over here I'm going to draw both coordinate systems kind of right on top of each other. So it's my y-axis and my x-axis. Okay. And now let's draw a point. Let's say we're talking about this point right here. If you were measuring the x and the y coordinates, the y coordinate is the distance measured down here. That's y. And the x coordinate would be the distance measured across here at a right angle. That would be x, right? So the x and the y coordinates there are given by those distances. Now let's put those in purple. Purple and purple. if you wanted to measure your position in polar coordinates, what you would do is measure along a straight line, straight back to the origin. That's called R. It is if you imagine that you at that point right there, at that point, if you imagine you're sitting on a circle, like if you imagine you're sitting on a circle which is centered at the origin. Okay, let's pretend you're on some sort of a circle there, and here's the circle, right? The R coordinate is the radius of the circle you would be standing on, okay? And then the other coordinate is theta, and theta is an angle in standard position, so therefore, measured from the positive x-axis that measures out to the ray that leads from the origin out to your position over here. So so there we go. So we have two ways of labeling the location of this point. One is x comma y, and that's rectangular coordinates. And the other is r comma theta, which is polar coordinates. Now, having drawn the x and y and the r and theta all on the same picture, sort of both coordinate systems superimposed on top of each other, what we can do now is actually use some trigonometry to figure out some relationships between these coordinates. So first of all, I have a right triangle here, right? X and y are the legs of a right triangle, and r is the hypotenuse. That's pretty useful. Theta is an angle in standard position. So it looks like if I were to do like the cosine and the sine of theta, I would get not exactly the x and the y coordinates, but pretty close, right? Because I would get the x and the y coordinates of a point on the unit circle. If the radius of the circle was 1, then the x and y coordinates would be exactly the cosine and the sine of theta. So what we need to do to adjust for circles of any radius is just scale by r. We need to multiply by r. What we're going to have here is a couple of formulas that we can use here. Is x is going to be not just cosine of theta, but r times cosine of theta. And y is going to be r times sine of theta. Okay, so there are two important formulas relating x and y to r and theta. Okay, so x is r cosine theta and y is r sine theta. By the way, if you divide both sides by r in either of these formulas, you get cosine of theta is x over r and sine of theta is y over r, and those formulas agree with the adjacent over hypotenuse and opposite over hypotenuse formulas for cosine and sine, respectively. So there we go. So that'll give us some important relationships, but there's a few others here we can get as well. For example, since these side lengths, since these three numbers are like the side lengths of a right triangle, they should also abide by the Pythagorean theorem. So one other formula we can use is r squared is the same as x squared plus y squared. And even if x and y are negative, that is still going to work because we're squaring everything, so it doesn't matter. And then the last one has to do with theta. If we say we want to get theta in terms of x and y, right? Well, we already did sine of theta, we already did cosine of theta and got these two. So what if we do tangent of theta? Well, tangent of theta is going to be y over x. And that is a pretty useful relationship as well. If you want to find theta for a given y and x, you can always do inverse tangent to get you to your theta value. Okay, with a slight adjustment potentially because of the restricted range of the inverse tangent function. So there we go. So this is your introduction to introduction to basic polar coordinates. So what we're going to do next is an example where we're just going to practice plotting points. We're going to plot points in polar coordinates. Okay, so I'm going to make a little polar coordinate grid over here. Okay, so this is not really a polar coordinate grid. Actually, all I have here is the x and y axes. But as you will see, that'll be sort of our starting position. So this is actually more like I've drawn a rectangular coordinate system, but we're going to draw polar coordinate points on top of this. So it'll make sense in a second. So all right, let's have our first point we want to draw. Let's have that be 0, 0. What is the point 0, 0 if we interpret that in polar coordinates? All of the points here are still going to look like ordered pairs, and it's still a number, comma, another number. And it's impossible to tell unless you are informed. It's impossible to tell whether this is in rectangular or polar. Okay, so it looks identical, so you have to be told. So I'm telling you to interpret these coordinate pairs as if they are polar coordinates, and that's how we're going to plot them. So this 0, 0 does not mean x is 0 and y is 0. This means that you are at a distance 0 away from the origin, and at an angle of 0. So an angle of 0 means we're not gonna go around the circle at all. We're staying on the positive x-axis, but then we're gonna travel out in that direction a distance of 0, which actually is gonna put us right here. So that point right there at the origin is our point A, 0, 0. All right, so this is useful because 0, 0, we're familiar with 0, 0 being the origin from the x and y coordinate system. So 0, 0 is still the origin in the polar coordinate system. Interestingly, if you do like 0 pi or something like that, or 0 any other angle, 0 comma theta, where theta is literally anything you want, that's still actually at the origin, because it doesn't matter what angle you traverse, what direction you point. You can point any direction and then travel distance 0, and you'll still be at the origin. So this introduces one of the weird quirks of polar coordinates, which is that there's actually more than one way to label any given point. This is different from rectangular, because in rectangular, if you have a point, there's exactly one x coordinate and one y coordinate that's going to correspond to that point. So the labeling in xy coordinates is unique. However, in polar, there's always going to be more than one way, if only because there's always more than one possible angle that would that would identify a given direction, right? And so coterminal angles means we're going to have multiple ways of representing the same point, but that's okay. Generally, for the origin, we stick to just using 0, 0. Okay, B. Let's plot the point 2, 0. Okay, so our angle is still 0, all right? Our angle is still 0, so we're still talking about pointing in the direction of the positive x-axis. But now we're going to find 2. Now I'm going to put some numbers on here. 1, 2. And I'm going to go ahead and do that for all my axes here, because I'm going to need those soon. Okay, 1, 2, 1, 2, -1, -2, -1, -2. So for point B, I'm going to point in the positive x direction and go 2 units, because r is equal to 2. So that would put me right here. So there is the point B. All right, for C, let's do the point 2 comma pi over 4. So we're still going 2 units away, but now we have to do pi over 4. So what we can do here is imagine that we're going to be on a circle of radius 2. So there's a circle of radius 2, okay? It's always centered at the origin. And then what we need to do is we're going to be on that circle, but we're going to measure an angle of pi over 4 in standard position. So pi over 4 in standard position is 45 degrees, so that would be this angle right here that goes out like that. There's pi over 4. And then we'll plot the point that's on that ray and also on that circle, and it's right there. So that's how you plot a point like that in polar coordinates, right? You're on a circle of a given radius, and you traverse, you move through an angle. Starting from standard position, you move an angle, and then you plot the point on the ray, on the terminal side of that angle, that is on the circle of the given radius. Let's do another one, D. Let's do the point -1 comma 2 pi over 3. Ooh, okay, so 2 pi over 3, first of all, is going to be, I'll use a pencil again. If I just extend this circle around, this is my radius 2 circle, but I'm just going to use it for a moment. So there's 1 pi over 3. There we go. There's 2 pi over 3. Okay, this line right here is my 2 pi over 3 line. But now my radius is negative. All right, here's another quirk of polar coordinates. Normally you think of the r value as being the distance away from the origin. However, it can be negative. And what that means is you're going to move backwards. So here's our angle, all right? There's our theta angle, 2 pi over 3. However, what we're going to do now is we're going to look back. We're going to travel the backwards direction. It's as if you turn your body. It's as if you turn your body to point in that direction, and then you walk backwards. Okay. I normally in the classroom I do this. I stand up and do this, but but here I'm just kind of like drawing with my fingers anyway. So what we want to do now is come back and put ourselves on a circle of radius 1. So there's the circle segment of radius 1. So this point D, so by the way, radius 1 because the absolute value of this number is 1, right? It's stepping back a distance 1. And so then that point right there is the point D. Okay. Let's do one more. Let's do E. We're going to do 1.5 comma -3. All right, so just a reminder, angles don't have to be nice clean fractions of pi. So -3 is a perfectly valid angle. -3 would be measured in the in this clockwise direction, or as one of my professors in graduate school once famously said, anti-counterclockwise direction. That's going to bring us right over here. Well, pi is 3.14, right? So it should bring us to a point that's sort of just shy of pi. And then what I want is that the reason I'm drawing the circle right here is because I want to be on a circle which is of a radius 1.5 because my r value is 1.5. So actually I didn't do a super great job. Let me fix this. Do a slightly better job of drawing that circle. Radius 1.5. By the way, what I'm doing in pencil here is all just kind of like not part of the actual graph, okay? So now I'm going to come in here and plot my point at radius 1.5 and angle -3 right there, and that'll be the point E. So yeah, so all these pencil rays and circles that I'm drawing, these are not actually part of the graph here. All I really should be graphing, they're just a guide, right? The pencil parts are just a guide. All I really should be graphing are these points. So let me go through here and so I hope you've got the right idea. Now I'm just going to go through here and erase the pencil marks. Okay, those really shouldn't be there. Okay, all that we really did here is just graph 5 different points, and there they are. There's the 5 points: A, B, C, D, and E. Okay, so that's all we got. All right, so there we go. So introduction to polar coordinates. In the next video, I'm going to teach you how to convert between coordinates, just kind of like converting between units.